Hello. Welcome to our new journey. My name is Mr. Dago and we are here to dive into the ocean of data structure and algorithms. So, let's get ready and make it possible. Bad programmers worry about the code. Good programmers worry about data structures and their relationships. Sneering face. Well, even though computers can perform millions of mathematical computations per second, when a problem gets large and complicated, performance can nonetheless be an important consideration. One of the most crucial aspects of how quickly a problem can be solved is how the data is stored and fetched from the memory. It is believed that data structures and algorithms are the basics of computer science. It is actual computer science. Any developer or CS student must write code that provides a required output. Algorithms are methods to implement certain tasks, while data structures are like hands for algorithms to make recipes. Using a combination of data structure and algorithms, we can improve the performance of programs drastically. Let's understand through an example. Once a fox invited a crane for dinner. The crane was joyful, but the fox only wanted to insult the crane. When the crane arrived, the fox served it a bowl of soup. It smelled delicious, but the crane's beak was ill-suited for a bowl. It could only snap its beak in frustration. Meanwhile, the fox lapped up the soup in minutes. The crane's algorithm to peck food was working on the wrong data structure. The crane gave up and took the fox's leave. However, before leaving, the crane invited the fox to dinner at its place. The fox immediately accepted. At the crane's place, the fox was served some fish in a jar. The fish waited invitingly at the bottom, which was out of the fox's reach. On the other hand, the thin jar opening was perfect for the crane. It pecked out fish with ease. That's what happens when you use the right data structure. An algorithm is a procedure that completes a task, like eating fish. A data structure defines a contract for storing, retrieving, and manipulating the data inside it. Choosing the right data structure for an algorithm is critical for its success. Since we live in the age of data, it's a good idea to familiarize yourself with the best ways to handle and organize information. More importantly, if you want to become a software engineer or a related data science professional, you need to understand concepts like data structure and algorithms. In this section, we are going to understand data structure concepts, including the definitions and importance. To understand data structures, we must first understand data. In the modern world, data and its information is an essential part, and various implementations are being made to store in different ways. Data is just a collection of facts and figures, or you can say data are values or a set of values that are in a particular format. A data item refers to a single set of values. In every programming language, we have some data types. For example, we have some data which has player's name Max and age 28. Here Max is of string data type and 28 is of integer data type. Suppose you go to the library and want to find a book on the 5th edition DSA, you'd go to the CS section. From there, you'd find the designated area set aside for DSA, then go through the books, sorted in chronological order, until you find the 5th edition. Now, consider books as your data, and the library's method of sorting the books as the data structure, and you're all set. In short, a data structure is a specific means of organizing data in a system to access and use. Let's have a look at the technical definition. Data structure can be defined as an arrangement of a collection of data items so that they can be utilized efficiently and the operations on data can be done efficiently. Therefore, data structure is all about the arrangement of data and efficient operations on the data. But the question is, where is it used? The answer is, inside the main memory, during the execution of a program. Every application will have a set of instructions that perform operations on data. So, data is mandatory. Primitive data type. Primitive data types are the data types available in most programming languages. These data types are used to represent single values. It is a basic data type available in most programming languages. Non-primitive data type. Data types derived from primary data types are known as non-primitive data types. Non-primitive data types are used to store groups of values. It can be divided into two types. Linear data structure. A data structure is said to be linear if its elements combine to form any specific order. In a linear data structure, only one data element can directly be reached. The common examples of the linear data structure are array, linked list, stack, and queues. Nonlinear data structure. In nonlinear data structures, the data values are not arranged in order and a data item is connected to several other data items. This structure is mostly used for representing data that contains a hierarchical relationship among various elements. It includes trees and graphs. Companies sell software to do more business. Amazon makes money from e-commerce, AWS, Microsoft makes money from Windows, Google makes money from ads, etc. How does a company develop software? Well, by software developers like you who code. What is coding? It is writing an optimized program using some language to achieve some task. How to write an optimized program? By learning data structure and algorithms. See? Here you can understand the chronology. Welcome to algorithms. You want to master this course, right? That means you want something done. Find a method or steps that will help you get your work done. We call this method algorithm. In simple terms, algorithm is a step-by-step process followed to do/accomplish any task. The best real-life application of an algorithm is you and me, i.e. the common man. Step 1. Start. You were born with a beautiful personality and came into this beautiful planet called Earth. Step 2. Happiness all around. Your entire family was happy with the aroma that came along with you. Step 3. Learning to walk and talk. You learn to walk, talk, run, laugh by failing so many times. Step 4. Join a school. You joined the school to get a quality education and learn what discipline is. Step 5. Learn to hold a pen and write. Excitement creeps in and you get a small joy while you are holding a pen and writing for the first time. Step 6. Years pass by. Few years down the line you realize that it is time to give exams and score good marks. Step 7. End of school. Your life as young ends and you step into college to see the real world and people. Step 8. College. You meet so many new people, you may join a course or choose a stream which you hate, but apart from that, you'll get enough time to party and have fun with new friends. Step 9. Career or fantabulous days are over. Now we'll get to know what politics is in our workplace, we'll meet flatterers. Step 10. Face dejection and disappointment. Think of steps 1 and 2, forget the disappointment and move on. Step 11. Gets old enjoying your time with your loved ones. Step 12. There is an end in life. In the end, you are with God. This is how the common man's life looks like. All this is nothing but an algorithm of every common man's life. An algorithm is a set of well-designed, step-by-step instructions designed to solve a problem or perform a specific task. An algorithm is not the complete code or program, it is just the core logic solution of a problem, which can be expressed either as an informal high-level description as pseudocode or using a flowchart. Suppose you want to add two numbers, the steps are crystal clear and there is no doubt. First, take number 1, then take number 2 and then add number 1 and number 2 as shown in the below image. Step 9. Career or fantabule. An algorithm is a set of well-designed, step-by-step instructions designed to solve a problem or perform a specific task. An algorithm is not the complete code or program, it is just the core logic solution of a problem, which can be expressed either as an informal high-level description as pseudocode or using a flowchart. Suppose you want to add two numbers, the steps are crystal clear and there is no doubt. First, take number 1, then take number 2 and then add number 1 and number 2 as shown in the below image. From the data structure point of view, the following are some important categories of algorithms. Search-algorithm to search an item in a data structure. Sort-algorithm to sort items in a certain order. Insert-algorithm to insert items in a data structure. Update-algorithm to update an existing item in a data structure. Delete-algorithm to delete an existing item from a data structure. Not all procedures can be called an algorithm. An algorithm should have the following characteristics. Input: an algorithm has some input values. We can pass 0 or some input value to an algorithm. Output: we will get one or more output at the end of an algorithm. Unambiguity: an algorithm should be unambiguous, which means that the instructions in an algorithm should be clear and simple. Finiteness: algorithms must terminate after a finite number of steps. Effectiveness: an algorithm should be effective with the available resources. Language independent: an algorithm must be language independent so that the instructions in an algorithm can be implemented in any of the languages with the same output. How do you measure your code? Would you clock how long it takes to run? What if you are running the same program on a mobile device or a quantum computer? The same code will give you different results. To answer these questions, we need to nail some concepts first, like time complexity. The time complexity is not about how long the algorithm takes. Instead, how many operations are executed. The number of instructions executed by a program is affected by the input size and how their elements are arranged. Time complexity, or running time, is the estimated time an algorithm takes to run. However, you do not measure time complexity in seconds, but as a function of the input. Why is that the time complexity is expressed as a function of the input? Let's find out. Let's say you want to sort an array of numbers. If the elements are already sorted, the program will perform fewer operations. Unfortunately, if the items are in reverse order, it will require more time to get them sorted. The time a program takes to execute is directly related to the input size and its arrangement. We can say for each algorithm have the following running times. Worst case time complexity, for example, input elements in reversed order. Best case time complexity, for example, already sorted. Average case time complexity, for example, elements in random order. We generally consider the worst time complexity as it is the maximum time taken for any given input size.